In 1961, John F. Kennedy set a seemingly impossible goal for the United States, where he said, "I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important for the long-range exploration of space. None will be so difficult or expensive to accomplish." And they did it. In less than 8 years. It proved when we commit to a goal, we are capable of achieving spectacular, seemingly impossible things. I'm Oscar Rapping. I lead Merck Animal Health Large Molecule Science and Technology Division. We set our own extremely ambitious, seemingly impossible goal. Our moonshot. Increasing the output of our production facility without increasing capital investments. The path forward was there in all the data we have available to us. But the big question was, do we leverage our data as effectively as possible to solve the many challenges we face in Merck Animal Health? In 2017, when we set this moonshot goal, the answer was no. Achieving our vision required a transformation towards smart operations that proactively uses data analytics to inform our daily decisions. We collaborated with the School of Industrial Engineering at Eindhoven University of Technology in the Netherlands to harness the power of cutting-edge operations research and operations management methods to complement our deep life sciences and biomanufacturing expertise. We are now 5 years into our collaboration, and we have successfully developed a portfolio of optimization models and decision support tools to meet our goal. Transforming science labs to smart operations is not easy. To date, competitive advantage in biomanufacturing has been primarily driven by the science. In other words, our knowledge of the underlying biological and chemical processes and how to exploit them to produce active pharmaceutical ingredients. But as market demand and competition have increased, the industry is now more sensitive to cost and production footprints. And accordingly, we are under a continuous pressure to make our biomanufacturing operations smarter, reducing cost and lead times to create critical medicines.
For more than 100 years, we have worked to make the lives of the animals around us better. Driven by a commitment to the science of healthier animals, Merck Animal Health offers veterinarians, farmers, pet owners and governments one of the widest ranges of veterinary products and health management solutions, as well as an extensive suite of connected technology that includes identification and monitoring products. Every year we produce over 102 billion doses of animal vaccines. We are present in more than 50 countries and continue to invest extensively in pioneering science and technological innovation, manufacturing products that are as innovative as they are effective, and deliver them through a modern global supply chain. We have been dedicated to preserving and improving the health, well-being, and performance of animals and the people who care for them. Whether it's on the farm or in the park, we strive to improve their lives as much as they enrich ours. Our facility in Boxmeer is Europe's largest biomanufacturing hub for veterinary medicines and the second largest in the world. In this facility, we research and develop new medicines and conduct large-scale manufacturing of more than 60 active ingredients. We produce a variety of medicines, vaccines to protect against disease, pharmaceuticals to treat disease such as antibiotics, and therapeutics to improve body function and provide benefits for a range of conditions. Insulin for diabetes, for example. We manufacture these medicines for 9 different species, serving over 150 countries worldwide.
Biomanufacturing is fundamentally different from conventional pharmaceutical manufacturing. We use living organisms to make active ingredients, rather than chemically synthesizing them. My name is Bram van Ravenstein, operational lead of the bacteriological production department of Merck Animal Health located in Boxmeer, the Netherlands. By re-engineering biological processes, we're able to generate highly complex molecules. An aspirin molecule is made up of 21 atoms, but a biopharmaceutical molecule might contain anywhere from 2,000 to 25,000 atoms. This increased complexity and sophistication results in an active ingredient that's functionally smarter, with higher efficacy and fewer side effects. For example, a biopharmaceutical can deliver instructions for the body's immune system to recognize a tumor and attack it without damaging healthy cells as chemotherapies do. Manufacturing biopharmaceuticals use the same techniques, equipment, and operational challenges whether the product is destined for humans or animals.
I am PK Yagneswaran. I lead Merck's Animal Health Manufacturing Science and Technology Group. The animal health industry faces significant pressures that make it critical for us to improve our biopharmaceutical manufacturing efficiency. First, most regulatory requirements between human and animal health are equally stringent. But animal health products may require additional studies to ensure food safety for human consumption. Secondly, market demand for animal health products is increasing. According to the United Nations Food and Agriculture Organization, the global population is expected to grow to almost 10 billion people by 2050. Robust agriculture production is a vital tool to meet the growing demand for food around the world. Veterinary vaccine demand is predicted to grow 10% every year for the next 5 years. Recent market analysis anticipate that the demand for animal products will double in developing countries by 2030. And the global demand for companion animals will grow exponentially during the same period. Thirdly, and probably most importantly, unlike human medicines that are often subsidized, animal owners are responsible for paying full price for these medicines.
Biomanufacturing consists of two production phases. Upstream processing, or USP, to produce the active ingredients, and downstream processing, or DSP, to prepare the end product and ensure it meets the desired quality and safety standards. In the USP phase, living organisms are cultivated to produce the active ingredients. The process begins with adding a seed culture, often a bacterial culture, but not always, and specially formulated growth media to a stainless steel bioreactor, equipped with sensors for real-time monitoring and control. The seed culture grows, cells divide and multiply, while producing an active ingredient via modern fermentation. The DSP phase begins after the batch is harvested. Solution collected from the bioreactor must be purified to separate the active ingredient molecules from the cells that made them and the media in which they were produced, without destroying their complex, fragile structures. Purification involves centrifugation, chromatography, and filtration. Purified active ingredient is then combined with inactive ingredients or formulated, filled, and packaged as appropriate. Every step is closely monitored to achieve the desired requirements on product safety and quality.
Biopharmaceuticals, or next-generation drugs, are among the most sophisticated and elegant achievements of modern science. Producing such large molecules reliably at an industrial scale leads to significant operational and technological challenges and requires sophisticated manufacturing capabilities unique to our industry. I'm Mark Bijens. I lead the Bioprocess Engineering and Innovation Division within Global Animal Health Manufacturing. Living organisms introduce high levels of uncertainty and batch-to-batch variability in production yield, growth phase duration, lead times and costs at all stages of the biomanufacturing processes. Product diversity in our manufacturing plants multiplies this already complex system. Each step adds to the complexity, the potential for variability, and requires precise planning and coordination. Given the unique challenges of biomanufacturing operations, a multidisciplinary approach was necessary to support our team's moonshot goal to improve production output. We collaborated with the School of Industrial Engineering at Eindhoven University of Technology. Operations Research, Operations Management, and Life Sciences joined forces to develop a portfolio of optimization models and decision support tools.
Eindhoven University of Technology is a research-driven university where excellent research and education go hand in hand. The Brainport region in Eindhoven is known for its excellence in top technology, and it's the heart of an innovation-driven industry. The engineers we educate are not only excellent technically, but they are also community-oriented. We understand that users and society at large must be considered when designing solutions. We stand out when it comes to collaborating with industry, translating our basic research into meaningful solutions for society. In our collaboration with Merck Animal Health, we develop models specifically tailored to the unique needs of the biomanufacturing industry. We use various operations research methods, including stochastic optimization, Bayesian learning, and simulation.
At Merck, we believe in One Health, an integrated approach to the health of humans, animals, and the environment we live in. By combining advanced analytics and operations research to improve biomanufacturing efficiency, our work influences all three aspects of the One Health concept. When we are able to produce more products without using more resources, we lower our carbon footprint as well. More products mean increased accessibility of life-saving medicines for healthier animals. Healthier animals mean a more sustainable food supply, protection against zoonotic diseases, a reduction in the burden of certain foodborne diseases, and longer and happier companionship for pets and their owners. Merck has also set several progressive environmental and social responsibility goals. We have committed to be carbon neutral in our global operations by 2025, reduce our operational greenhouse gas emissions by 46% by 2030. At the same time, we have also committed to improve global access to health by reaching at least 75% of countries around the world annually with our products, enabling 100 million more people to access our innovative portfolio and reaching 100 billion more animals worldwide.
So this was our moonshot. How can we deliver affordable medicines to more patients and animals and reduce our environmental footprint at the same time? To achieve our moonshot and our vision of smart biomanufacturing, we conducted 3 major projects. Our first project reduces bioreactor setups through a novel technology called bleed feed.
Bioreactor setup involves several activities and is a critical component of upstream processing, accounting for as much as 25% of the total bioreactor processing time and cost. Bioreactors need to be cleaned and sterilized after each use. Seed culture and media must be prepared, and other necessary instruments, such as sensors, must also be equipped. All of these activities require highly specialized labor and materials, and are well known to be costly and time-consuming accordingly.
Once the bioreactor is set up, the fermentation process starts. Cell growth follows a specific pattern during fermentation. Initially, cells enter a lag phase, followed by an exponential growth phase. Finally, they enter the stationary phase, in which growth flatlines.
To reduce the time and effort spent on a setup, we implemented a technique called bleed feed, a novel technique in life science literature, especially in the context of batch fermentation. Instead of harvesting the entire batch at the stationary phase, a fraction of the cell culture is extracted during the exponential growth phase, and a special medium is added. The remaining cell culture acts as a seed for a new bioreactor run and continues to exponentially grow to create another batch. If the bleed feed is performed successfully, the setup of the next batch can be skipped entirely. An opportunity to reduce bioreactor cost and lead times significantly. There are constraints though. Primarily, the bleed feed can only be performed in the exponential growth phase, before the stationary phase. However, the duration of the exponential growth phase is uncertain. We don't know exactly when the growth rate will transition into the stationary phase.
This uncertainty introduces a compelling trade-off between bleed feeding too early versus too late. We are playing a bleed feed or no bleed feed game here. If we carry out the bleed feed too early, we will not obtain the maximum yield from the batch. If we run it too late, cells enter the stationary phase and we incur the penalty for setting up a new batch.
We piloted the bleed feed technique in 2015, based on our domain expertise in life science. Preliminary test runs failed because we couldn't identify the optimal bleed feed time. Additionally, strict regulatory requirements stipulate that bleed feed can only be performed once or twice. All these factors made us question the value of adopting this technology.
What we needed was a production guidance specific to a bioreactor and product that could tell us when to bleed feed. How can we generate an optimum bleed feed policy? What are the potential benefits of bleed feed? To answer these questions, we needed a method that addresses the trade-off between risks and rewards, perfect for Markov decision processes or MDPs. We have built a discrete time, finite horizon MDP model and calibrated it with real-world data. The fermentation process is monitored at discrete time intervals called decision epochs. In practice, these decision epochs could be every minute, hour, or day, depending on the specific application. The state space of the MDP model represents the key parameters for decision making. In our case, there are three critical components. First, we monitor the age of the cultivation. This is denoted by the state I. Second, we capture the growth rate mu of the cell culture. And third, we record the number of bleed feed operations N performed so far. At each decision epoch, we have two actions. We can either continue the fermentation over the next decision epoch or perform the bleed feed. Kinetic models from life science describe how the fermentation process evolves over time. However, they are deterministic and they do not reflect the inherent uncertainty of the fermentation. This is where life science and operations research join forces. The state transitions of the MDP model expand upon the kinetic models in life science. We capture the probability of entering the stationary phase at time I+1, given that the process is in the exponential growth phase at time I. Our goal is to maximize the active ingredient production per setup. This is captured in the value function of the MDP model. If we continue the fermentation, we produce additional active ingredients, which is the immediate reward of the MDP model. But we risk entering the stationary phase. If we decide to bleed feed, the cultivation age resets, we have uncertainty in the growth rate of the subsequent batch, and the bleed feed count increases by 1. This model captures the tension between increasing the yield and increasing the failure risk by delaying the bleed feed time. By optimizing the bleed feed process in Boxmeer, we achieved around 82.5% higher yield per bioreactor setup.
We also analyzed the structural properties of optimal bleed feed policies and showed they have a control limit structure. On the x-axis, we have the age of the fermentation, and on the y-axis, we have growth rate. In this figure, we see that the state space is partitioned into two distinct regions, continue and bleed feed. If the current state of the batch is in the bleed feed region, then we perform it. Otherwise, we continue the fermentation. From a practical perspective, these control limit policies are easy to explain and implement in our daily operations. Once tested and implemented in Boxmeer, we began an international knowledge transfer. We immediately started a new bleed feed implementation project at another facility in the United States. Because we now have more experience in both the theoretical and applied aspects of bleed feed, we have iterated both our modeling and analysis in the US facility to continuously improve. We expanded the model scope to capture uncertainty in growth inhibitors, substrate and impurity concentrations during fermentation. In addition to pinpointing the optimal bleed feed time, we have also optimized the bleed feed amount, which resulted in a productivity increase of 50 to 70%.
Our second project was focused on optimizing the critical process parameters of fermentation.
Once a bioreactor is set up for fermentation, we are naturally incentivized to achieve the highest possible production yield from that batch, with the lowest variation possible. The box plot in this figure shows the mean and variability of annual production yield obtained from 3 production lines, lines A, B and C. The only difference between these 3 production lines was the bioreactor type used and its corresponding mixing mechanism. This implied there was a controllable process parameter we could adjust to achieve the best performance from line C. There was no literature available to inform how production yield would change as a function of this controllable process parameter. We needed to conduct several experiments. but they needed to be done at industry scale, where there's little to no room for mistakes. We were faced with an optimal learning problem, quantifying a biological relationship between the controllable process parameter and yield through a minimum number of experiments.
We have built a Bayesian design of experiment framework that helped us identify the best process configuration based on both expert opinion and real-world production data. We knew the batch yield will be concave as a function of the controllable process parameter. We had a hypothesis for the optimum value of the process parameter, but did not know the precise shape of this function to predict the peak point. We scaled the solution space of this search algorithm based on our expertise in this domain, and we were able to establish a targeted range. As an output, the Bayesian design of experiment approach helped us generate an information collection policy. In total, we conducted 8 industry-scale experiments to identify the best process configuration, resulting in a 50 to 60% higher yield per batch by simply adjusting a critical fermentation process parameter. Additionally, by standardizing this parameter, we reduced the batch-to-batch variability from 25% to less than 5%.
And our last project was to establish an end-to-end visibility of our manufacturing operations and improve our scheduling decisions.
Before we describe the solution, we need to revisit the scale and complexity of our manufacturing operations in more detail. In our Boxmeer facility, every day, our manufacturing system consists of 8,000 interdependent process steps to produce 60 active ingredients critical to a range of medicines. This work is split across multiple semi-autonomous process lines, where each line has a similar flow, but the sequence and cycle time of the steps vary between recipes, even for the same product. A recipe in this context describes the manufacturing steps from the starting material to the final active ingredient through one particular production path, consisting of 200 to 300 interlinked tasks. Complexity in our production environment is driven not only by the large number of steps, but also several critical manufacturing characteristics and their interdependencies. The same product can be produced with different recipes or alternative production paths. Some products have preferred paths, and not all paths have the same yield. For most of the steps in the production line, a zero wait time constraint is in place. There are only few steps where the work in progress can be stored to wait for a resource to become available. Since each production line has multiple bioreactors, we often implement parallel starts, where more than one product start occurs simultaneously, or overlaps with another start. Once one manufacturing action is completed, the solution is passed downstream, the resource is reset for readiness, and then used for another manufacturing activity. The next start decision does not wait for the pipeline to finish. If the first start runs slower than the next, they may compete for the same downstream resource. Prior to starting this work in 2017, we didn't have a systematic approach for using real-world data to support our planning and scheduling decisions. At that time, planning and scheduling took place manually in an Excel sheet. We needed to build a more reliable solution, dividing the work into 3 phases.
For phase 1, we systematically collected and organized all the relevant data to create end-to-end process maps and analyze the complex interdependencies for each of the 8,000 production steps. This data includes details like bioreactor processing time, which products can use which bioreactor, batch quality, yield, and much more. In the second phase, we built a discrete event simulation model, using the data from phase 1, resulting into the first end-to-end view of our facility operations. This allowed us to run what-if analysis in a simulation model and increase our output without expanding our capacity. Finally, in phase 3, we developed a fully custom schedule optimization model. The overall model consists of high-level and low-level optimization. The low-level optimization is on an individual task level and optimize each recipe individually. To understand the optimization function, let's first consider the input parameters. We map all the factory details and limitations to create the constraint space. We account for the daily number of equipment and personnel available, as equipment can be unavailable due to preventive maintenance, and personnel have their individual specific working days. Each person's availability is further influenced by their shift schedule, flexible break times, their skill set, and non-production related activities. The recipe details create a solution space. This includes task-related target duration and ranges, resource requirements, and interdependencies with other tasks. Together, the constraint and solution space define the optimization plane, where the objective is to minimize make span, fulfill demand on time, and meeting target durations as close as possible while satisfying the constraints. The high-level optimization combines this detailed recipe and constraint information with the current schedule, inventory, and upcoming demand. You can see this high-level optimization as a game of Tetris, where each recipe is simplified into a uniquely shaped block representing the occupation of multiple resources over time and with a specific yield. The field represents all the available resources and corresponding constraints. We progress in the game by filling all the available spaces in the field with Tetris pieces needed to fulfill demand on time. As in Tetris, the field changes over the schedule horizon due to daily resource availability and already placed Tetris pieces. So to fulfill demand of one product, different Tetris pieces can be used over time. These specific Tetris pieces and their corresponding timing relate to specific products made in a specific batch size following a specific production path to fulfill demand over time. However, as these Tetris blocks are a simplified representation of the actual detailed recipe information, the high-level optimization will result into multiple scenarios and pass these on to the low-level optimization. From the high-level scenario, the order, batch size, rough timing and recipe of each product are known, but the low-level optimization will determine the specific timing of each individual task within each recipe. As this optimization model optimizes each recipe sequentially, the sequence of optimizing recipes is of influence. Therefore, the model creates up to 100 different low-level scenarios for each high-level scenario. After scheduling each low-level scenario, the model will also make sure each operator stays cross-trained, minimize task switching between operators to ensure batch ownership, and utilization is balanced across operators. Each scenario is then evaluated against performance indicators like make span, fulfilled demand, and weekend work. Finally, operator-specific daily task lists are generated to execute on the optimized schedule. The result of the low-level optimization is also fed back into the high-level optimization to train the algorithm that created these simplified Tetris blocks, which improve the accuracy and speed of the model over time.
The models we have developed to improve bioreactor yield and production scheduling have been implemented in our daily operations and generated a significant impact. By optimizing the bleed feed process alone, we achieved around 82.5% higher yield per bioreactor setup. By optimizing the critical parameter configurations, we realized a 50 to 60% improvement in batch yield. Standardizing these parameters improved our batch yield standard deviation by 20%. Finally, our optimized end-to-end planning and scheduling allowed us to produce an extra batch per week per production line across multiple production lines. Combined, we have produced $200 million worth of revenue, with more to come without additional raw materials, energy resources, new equipment or facility space. Merck Global Animal Health is a $4.7 billion business globally. The additional revenue alone from Boxmeer are equivalent to 4.25% of our global revenue. But beyond the direct results in our biomanufacturing productivity, we have benefited internally and made huge strides on our journey towards One Health. We established a new operations research team within Merck Animal Health to support this more prominent role in our organization. We created 10 new positions for industrial engineering master's students, most of whom have continued as a full-time employees. We now require 40% less energy to produce the same volume of product, saving 240,000 cubic meters of gas and 1.2 million kilowatt hours of electricity and reducing our carbon emissions with 468 tons of carbon dioxide emission and environmental footprint accordingly. The animal health industry at large cannot currently produce enough supply to meet market demand worldwide. Every additional unit produced makes a difference in delivering our life-saving medicines more accessible and affordable to our patients and animals around the world.
We would like to also emphasize that One Health is not limited to Merck. The United Nations recognizes One Health and has called for urgent adoption of integrated human, animal, and environmental health expertise and policy. One driving force behind this call to action, which is particularly relevant now, is pandemic prevention. The World Health Organization estimates that 61% of all human diseases are zoonotic in nature. They are transmitted from animals to humans. 2 million people die each year from neglected endemic zoonotic diseases such as anthrax and rabies. The Nature Journal in 2022 has published convincing new evidence that the current COVID-19 pandemic was initiated by zoonotic transfer, presumably from bats to humans. In the last century, we had 6 major outbreaks that were zoonotic in nature, including Ebola and SARS. Merck Animal Health plays a critical role in preventing zoonotic disease transmission and maintaining the health and welfare of humans and animals together.
When we began, our moonshot was to increase the output of our production facility without increasing capital investments. Not only did we realize that vision, we intended to scale our entire global animal health manufacturing network, multiplying our energy savings by 6.5 times to 1.56 million cubic meters of gas and 7.8 million kilowatt hours of electricity, and creating an additional $1 billion worth of life-saving veterinary medicines. We can implement these process improvements in human health manufacturing as well, further multiplying the positive impact to environmental sustainability and enhancing global access to health. We believe we have an ethical responsibility to continuously improve and share these methods and our expertise with our global community. We have been pioneering the application of operations research in the biomanufacturing industry. Through the work we have presented, we have proven that linking operations research with life sciences in biomanufacturing drives substantial, sustainable, and scalable productivity improvements. We are certain our work will inspire the global manufacturing industry and stimulate new research at the intersection of operations research and life sciences to advance the field. Together, we can achieve a new moonshot to drive these innovations globally and accelerate our course towards One Health. Together, we can make this world a better place for all.